So now we're going to look at Newton's second law for rotation. We've spent quite a lot of time looking at Newton's second law for the translational case. So we're all quite comfortable using that the net force is equal to the sum of the forces acting, which is equal to the mass times the acceleration. Now for the rotational case, there's an analogous equation. We've got that the net torque is equal to the sum of all the torques acting, and this is equal to the moment of inertia times alpha, the angular acceleration. So let's consider the simplest case and see if we can show this equation. So imagine that we have a massless rod of length r and we place a mass m, a point-like mass, on the end of it, and then we apply some force to that mass. Now we'll let our rod have an angle theta with the horizontal, and we'll let the force have an angle phi with the radius, the length of the rod, as shown in the figure. Now if we want to calculate the torque that this force causes, we can use that the torque is equal to r cross f, which is equal to rf sine phi. Phi here is the angle between the radius and the force, just like we've shown in the diagram. So this is actually equal to r times the tangential component of the force, as we can break that force into a radial component and a tangential component. So the tangential component of the force is equal to the mass times the tangential component of the acceleration. That's just an application of Newton's second law for the translational case, and we have seen that the tangential acceleration is given by alpha times r, where alpha is the angular acceleration. So let's put all of these together now. We've got that our torque is equal to the radius times the tangential force, so the torque is equal to the radius times m times the tangential acceleration. So the torque is equal to the radius times m times alpha times r. Or we can rearrange that to write it as mr squared alpha. Now for the object we've just described, a massless rod with a mass m on the end, a distance r away, the moment of inertia is just given by mr squared. So you can see in this case the torque is equal to I alpha. But is this generalizable, or have we just shown it for the simplest case? Well, we can actually extrapolate this for all cases, because whenever we're considering a continuous body, we just break it up into lots of little components and add all those components together. So by showing it for one small component, we can actually extrapolate this to whole continuous bodies. So the generalizable formula is that the net torque is equal to I times alpha. So let's have a bit of a look now at a physical example where we can actually make use of this equation.